Welcome to Maths with EJD. In this video, I'll be talking about binomial expansion for negative and fractional exponents. In the first video, we talked about the use of Pascal's triangle for binomial expansion. And you'll discover that in using Pascal's triangle, right, where you had, power of zero, you have just one coefficient, which is one. Power of one, you have two coefficients. Power of two, you have three coefficients. That's one plus one, two, then one drops. Then power of three, you have one, and then you have one plus two, three, two plus one, three, and then this one drops. Then you have power of four, you have one here, one plus three is four, three plus three is six, three plus one is four, and one like that. So that was Pascal's triangle. So you discovered this was only possible for whole numbers, right? So it's only possible for powers starting from zero upwards. Now, in the second video, we went ahead to talk about the binomial formula. So we had the binomial formula. And for the binomial formula, the expansion was something like this, that if you had a plus b raised power n, and then that will be equal to summation from k equals 0 to n of, n combination k, then you have a raised power n minus k, b raised power k. So in this case, because of this part now, which is actually combination part, because it's combination part, right? Usually it would require you to have a positive n. So just like up here, positive power is required, for Pascal's triangle. Positive power is required. I mean, positive and whole number power. Then here too, positive power is required. Positive power required. Now, what if you now have a situation where you have to say you want to expand like a plus b raised to power half, or a plus b raised to power minus half, or a plus b raised to power, say, minus 5. With all the Pascal's triangle and binomial formula will not be able to handle that. And that is why this particular uh, video is necessary. So we're talking about binomial expansion for negative and fractional exponents. So we see that binomial theorem, the binomial theorem is typically expressed, is typically expressed for positive integer exponents, just like I've explained, for positive, not negative, right? It can be negative and it can be anything apart from integer. For positive integer exponents n. Okay. However, let me take that down. So, however, it can be extended to cases where n is a negative, where n is a negative or fractional number. It can be a negative number or a fractional number. And this we can do, fractional number, this we can do by deriving. So we can derive an infinite series expansion. Infinite series expansion. And that would seem to be a kind of general way of, so, and this infinite series expansion can take care of both positive integers, negative integers, or even fractions generally, right? So, however, it can be extended to cases where n is a negative or fractional number by deriving an infinite series. So the key word here now is the infinite series. By deriving an uh, infinite series expansion. I meant to write that here, infinite series expansion. Okay, so here the key is the infinite series. Now, this extension this extension is valid under, so it's only valid under the convergence criteria, under the convergence criteria, which is that the absolute value of x is less than 1. And of course, the way to interpret this is that -1 is less than x is less than 1. So this is the condition for this to hold. So once x that means that x is greater than -1 and x is less than 1, right? So once x is less than -1 and x is greater than 1, this law breaks down. Okay, so let's now look at the general formula for the infinite series. General formula for the infinite series. Okay, so this is like one solution to every problem of binomial expansion you will ever have. So for 1 plus x raised to power n, where n is not a positive integer, where n is not a positive integer, the binomial expansion is given by, so now we can no longer use that combination thing we saw the other time. So it's given by 1 plus x raised to power n, and see how this progresses. So this will be more something like, as usual, if you like, I think that can be 1 raised to power n, x raised to power 0. I know all of that is going to be 1. This over 0 factorial for easy understanding. Then plus 1 raised to power n minus 1. Of course, the power of 1 will start reducing, while the power of x will start increasing, will be increasing. So x raised to power 1. So at every point in time, n minus 1 plus 1, or n plus 0, all of that should give you n. So this is about 1 factorial plus 1 raised to power n minus 2 x. Okay. I forgot to do this. Okay. So after the first one, right? Then you have this power n comes down, and then you have 1 raised to power n minus 1, x raised to power 1, all over 1 factorial. Next, you have this n into the power of 1 now, n minus 1, into 1 raised to power n minus 2, then x raised to power 2, all over 2 factorial. Then you can go on and have, so now you have n into n minus 1 into n minus 2. So this n minus 2 up there now, it now comes down here. So you have 1 raised to power n minus 3, then x raised to power 3, all over 3 factorial. Okay. Then you can go on and have n into n minus 1 into n minus 2 into n minus 3, then 1 raised to power n minus 4, into x raised to power 4, all into x raised to power 4, right? All over 4 factorial. And that can go on like that. So you just keep following this pattern. And this is a general formula for the infinite series expansion for fractional or negative powers. So this is the summation. So you can have that, right? Or in summation, we can then have what we're used to, which is this 1 plus x raised to power n equals summation from k equals 0 to infinity of n combination k x raised to power k. So this is like the summary of it, but then with a little bit of twist. So because that combination part is now specially designed to handle negative values or fractional values now. So where the generalized binomial coefficient is, then you now have n combination k is now, instead of just what we're used to, so say n into n minus 1 into n minus 2. So it's just the normal thing also, except that now you have you can actually have n to be fractional or negative number. So this over k factorial, that's what we've had there. And we also know that this series converges when one lies between x and 1. When x lies between -1 and 1, that's, in summary, absolute value of x is less than 1. Okay, so in the next video, we can talk about how to derive this. Okay, so let's just go ahead. We've talked about the convergence criteria. Okay, I mean, what this simply means is that the infinite series, just like we said here, the series converges when absolute value of x is less than 1. And this is because the terms decrease, in magnitude rapidly for absolute value of x less than 1, ensuring the sum approaches a finite value. All right, so after now, let's look at the examples to drive the point home. So I think I'm going to take two examples, one for fraction and one for negative power. So example 1. So um, expand 1 plus x raised to the power half. Okay, we need to expand this. Let me write it more clearly. Expand 1 plus x raised to the power half. Absolutely, Pascal's triangle cannot do this, and the normal binomial formula can also not do this. So what do we do here? Okay, expand 1 plus x raised to the power half and use it to estimate. Is it to estimate 1.1? Is it to estimate 1.1 raised to the power half? Use it to estimate square root of 1.1. Okay. So we do this and then we use it to estimate square root of 1.1. Let's see how that works. Okay. Now, from what we have already, right? This is 1 plus x raised to the power half, the solution now. 1 plus x raised to the power half. So that means we are going to have, based on what we had there, so this is 1 raised to the power half, okay? Then x raised to the power 0 all over 0 factorial. Plus, next thing, the power half comes down. So you have half here into 1 raised to the power half minus 1. Okay, that's half minus 1. X raised to the power 1 all over 1 factorial. I mean, subsequently, I may not show all these steps, or maybe I will, let's see. Okay. Okay, let me just do it straight so that I won't have to, because whatever I have up there is going to be needed at the next step. So, but I can do it by the side. So I know half minus 1 is like this. LCM is 2. 2 into 2 is 1. 1 times 1, 1 minus 1 into 2. So this is minus half, right? So this is 1 raised by minus half x raised by 1 all over 1 factorial. So next, you have half multiplied by minus half, that power up there. Then you have 1 raised by minus half minus 1, minus half, minus 1 over 1 again. LCM is 2. 1, 2 into 2 is 1. 1 times minus 1, that's minus 1 minus 1 into 2. So that's minus 3 over 2. Okay. So this is minus 3 over 2 x raised to power 2 all over 2 factorial. Okay. So we see there's a particular pattern it's following. So we can follow the trend now. So let me get like 5 terms. I have 3 terms already. So the fourth term now is going to be half. So this plus half into minus half into minus 3 over 2. That's that power, this power now. Then 1 raised power minus 3 over 2 minus 1. That's minus 5 over 2. So into x raised power 3 all over 3 factorial. So let me get the last term. So that will be half, the first half that we had from the beginning into minus half into minus 3 over 2 into minus 5 over 2. Then 1 raised power minus 7 over 2 because minus 5 over 2 minus 1 is minus 7 over 2. Then x raised power 4 all over 4 factorial, and all of that continues. So we can try to tidy this up now. Let me switch to the green. So now I have 1 plus x raised power half is equal to, so now first of all, anything raised power, 1 raised power anything is 1, right? 1 raised power half, 1 raised power minus 1, 1 raised power 1 million is always 1. So you can cross out this so that it doesn't confuse you. And some people can get, they can stumble over this. So just know that that is 1, okay? So in that case now, so the first one is 1 raised power half. We know that is 1 already. X raised power 0 is also 1. 0 factorial is 1 down there. Then you have plus half into 1 raised power minus half is also 1. X raised power 1, that's x, all over 1 factorial is also 1. Plus half into minus half. Then 1 raised power half, 1 raised power minus 3 over 2 is 1. Then we have x squared all over 2 factorial. Then when we come to the next one, we have 1 over 2 into minus 1 over 2 into minus 3 over 2. Then 1 raised power minus 5 over 2 is 1. Then we have x raised power 3 all over 3 factorial. Okay, I guess we can tidy that up already. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. Okay, so we go for the fourth one. So this is half, then minus 1 over 2, minus 3 over 2, minus 5 over 2. All right, then 1, 1 raised power minus 7 over 2 is 1. Then we have x raised power 4 over 4. Okay, 4 factorial is 4 times 3 times 2 times 1. And all the terms continue like that. Okay, so we are still on the matter. Next thing we have is 1 plus x raised power half, still tidying things up. So 1 times 1 over 1, all of that is 1. So next we have plus half x, half times x, that's half x. Then look at this now. This is, so, okay, to make things easy, right? Let me still do this. So half times minus half is minus 1 over 4, okay, all over 2. In fact, okay, all over 2, let me just do it that way. Then we have x squared. Then next, we have plus, minus and minus is plus. So we have 1 times 1 times 3, that's 3. 2 times 2 times 2, that's 8. So we have 3 over 8 x cubed all over 3 times 2 times 1. That is actually 6. Then the last one here, we have half minus times minus and minus, that's negative for sure. Then half times half is 1 over 4. Okay, or let's just do this. 3 times 5 is 15. So we have minus 15 up there, all over 2 times 2 times 2 times 2, that is 16. That's 2 times 2, 4 times 2, 8 times 2, 16. Then x raised to power 4 all over 4 times 3 times 4 times 3, 12, 12 times 2, 24, 24 times 1 is 24. And this goes on like this. And then we switch again. So now things are getting tidier. So we have 1 plus x raised to power half is equal to 1 plus half x. And to make this make more sense, all this divided by half simply means you have half multiplied by minus 1 over 4 of the x squared plus, then this 6 is actually 1 over 6 into 3 over 8 x cubed, then plus this 1 over this over 24 means we have we can say it's 1 over 24. Okay, so this is 1 over 24 into minus 15 over 16, x raised to power 4, and all of that goes on. So things are tidier now, so we can go further and simplify. 1 plus x raised to power half, that is 1 plus half x, then plus and minus, that's minus 1 times 1, 1, 2 times 4, 8. So 1 plus half x minus 1 over 8x. Then here 3 is 1. 3 and 6 is 2. So we have 1 times 1 there. That's 1 over 2 times 8 is 16 x cubed. Then here we have what can go? 3. 3 here is 5. 3 here is 8, right? Yeah, 3 goes in 24 8 times. So plus and minus, that's minus 5 over 8 times 16. 8 times 16 is like 4 times 16 is 64. So that's like when I was doing mental matrix, right? 8 times 16 may not be that easy, but I know that if I remove 2 from 8, that's 4 times 32. So and that's easier, which is 96 now. All right. Or 8 times 6 is 40. No, 4 8 times 16 is the same thing as 4 times 32. So 32 times 4 is 32 times, so that's like 128. Or better still, 4 16 is 4 times 4 times 4, that's 64 times 2, that's 128. So I have minus 5 over 128 x raised to power 4 plus all this. So that's the result. All right, this is the result we actually are looking for. This now, this is the results we need. Okay, now that we have this, we are required to estimate. So we can say to estimate square root of 1 plus 1.1. Okay, that's the next thing. So you know that square root of 1.1 is equal to 1.1 raised to power half. Okay, 1.1 raised to power half. So what's the connection between this? So the other thing, the original thing we had was 1 plus x raised to power half. So, how does this compare? So we have compare 1.1 raised to power half with 1 plus x raised to power half. So you can see everything looks alike. So automatically, it means that 1.1 is the same as 1 plus x. So it means the things in brackets are the same because the power are the same. So in that case, now we can just say that 1.1 minus 1 is equal to x. So that means that x is equal to 0.1. So since x is equal to 0.1 now, and you want to use the expansion to estimate, so you can bring the expansion now. I can stop at the fourth term instead of going all the way down. So using the first four terms, using the first four terms, so we have that 1 plus x is equal to 1 plus x raised to power half. That is 1 plus x raised to power half is equal to what now? 1 plus x raised to power half. That is equal to 1 plus half x. This 1 plus half x. All right. Then minus 1 over 8x. Okay. Then plus 1 over 16. I want 1 plus 1 over 8x squared, that is. All right, so this should be 1 over 8x squared. Where do we have? Yeah, it's x squared. 1 over 8x squared. Then plus 1 over 16x cubed. So that's plus 1 over 16x cubed minus everything that follows. Okay, all the other things follow like that. So let's use this. So that means that square root of 1.1 is the same thing as 1 plus 0.1 raised to power half, because x now is 0.1. So anywhere you see x in this expression now, you put 0.1. Okay, so that we now have 1 plus half into 0.1 minus 1 over 8 into 0.1 squared plus 1 over 16 into 0.1 cube. Okay, so that now is equal to Okay, now it's approximation, right? So it's approximation. So this is so square root of 1.1 is approximately 1 plus square root of 1.1 is approximately 1 plus 0 point half times 0.1. That's like 0.1 divided by 2. And that would be 0.05 minus okay, let me try to spell this out as much as possible. So this is 0.1 all over 2 minus 0.1 squared. That's 0.01 divided by 8 plus 0.001 divided by 16 minus whatever follows. We're just we're approximating this divided by 16. So it means that square root of 1.1 is approximately 1 plus 0.1 divided by 2 is 0.05. 0.01 divided by 8, that is 0.00125. Then plus 0.0000, that's 4 zeros, 25. Okay. And that means the square root of 1.1 is approximately 1.048775. 1.048775. And this is the result we need. This is the result. 1.048775. Okay. That's the result we need. Now, because this video is getting too long, I think I'm going to do negative power. I've done fractional power here, so I'll do negative power in the next video. So I'll just stop here. But let me punch a calculator to see what this actually should be. Square root of 1.1. Normally, what is it? Of course, here, because we are just estimating, so we don't expect it to be exactly what the calculator will give us. So square root of 1.1 is equal to, yeah, so square root of 1.1 using calculator, square root of 1.1 is actually 1.0488. If we take it to 6 decimal places, 1.0488088. So you can see it's somewhat close. But I mean, it's a good estimation. At least it is correct to like two or three decimal places. Yeah. So not a bad idea. So if you want the more accurate you want your estimation to be, the more terms you need for the expansion. So let me do the fractional part in the next video. No, sorry, this is the fractional part. I'll do the negative part in the next video. So subscribe to this channel if you haven't done that already, and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are, and let me also know if you have a topic for me to teach or a a problem to solve. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing math right. Bye.